Remember right here, piecewise defined function? I tried to explain it to you using a map. And the idea is that, like, if this is supposed to be a map of America, and the idea is that on different pieces of the function, different places, the function is defined to be different. Okay. So we want to use this idea as well, but we're not going to have our domain be America. Our domain is going to be a mathematical domain. Okay. So if we go to our worksheet over here and we look at our piecewise defined function, there's two pieces. And we kind of chopped it up into two different regions. Okay. So, oh man, you know what? I'm gonna come back to example 4 because I want to talk about shifting. I want to talk about transformations first. After I talk about transformations, it'll be easier for us to graph this guy here. So stay tuned. Sorry, I kind of hyped it and then I said we'll get back to it. Um, so let me tell you what we want to do first before we graph that. What we want to do first is I want you to imagine you have some basic function like x squared, and then we could transform it in different ways. And what we want to do is we want to see if I change the algebra of the situation, which would be the left column over here, then what happens to the graph? What's the effect of the graph of the function? And that'll be in the right column. Okay. So when you look at this, there's two instances where you have this plus c. Right here, you have a plus c. Right here, you have a plus c. So what's the difference between this first one and this second one? Do you guys know?
Is it if the plus c is outside of the fx, you move up and down, but if it's inside with the x, you move left and right.
Correct. Absolutely. So the comment that I want to make is what you call up down, I call those vertical. So this is vertical, and the stuff that you're calling left right, which I like, I mean, I'm going to call that horizontal. So I really like what she said. She said that if the plus c, or in this case minus c, is outside of the function, it's a vertical thing. If it's inside of a function, it's a horizontal thing. Okay, that's that's important. So look at this guy right here. Do you think this is a vertical thing or a horizontal thing? It's vertical, right? Because it's outside the function. So this is vertical. And what about this guy? This guy is inside. Do you see how it's inside the function? So it's gonna be a horizontal thing. Again, this guy is outside. The negative is outside. So it's gonna be a vertical thing. And if the negative inside, that's gonna be a horizontal thing. So I think that's key. Like that's key to understand that that's what's going on. Okay. So I'll probably erase those red words, but I just wanted you to see, notice that pattern, first of all. So when I go to talk about these transformations, the plus C is basically going to be a vertical shift. Up by C units. And then if it's negative C, then there'll be a vertical shift, but it'll be down C units. Okay. If you have a plus C on the inside, do you think that's going to be a horizontal shift left, or is that going to be a horizontal shift right? Any thoughts?
Left to the right.
You want to guess again? It's actually to the left. So the horizontal stuff actually works kind of the opposite way that you would think. Um, and we're going to see that show up again. So it's actually the minus C that shifts it to the right. So this is a horizontal shift to the right. Okay. So I kind of want to tie this back to the beginning of the class. So check this out. Remember I was talking about this. At first I was looking at this graph is like absolute value graph, or this is an absolute value thing. And this is absolute value of x minus 2. So when I see this x minus 2, I'm thinking a horizontal shift over by 2 units. So if you look at our picture, we started off from -1 to 1, but if we shift everything over to the right by 2 units, we go from 1 to 3. So this can be thought of as a horizontal shift. Instead of finding the distance from 0, find the distance from wherever we shift it to. Does that make sense? Okay. So we have that. All right. So do we see any other examples over here? Let me just scan real quick. Nope. Oh well. Oh, we did see one. Did we? Where's the equation of the line? So like, well, never mind. Forget it. That's not, I don't want to confuse you, so it's not important. Let's continue talking about our transformations. The next guy, if you multiply by C, because you're multiplying outside of the function, that's going to be a vertical thing. That's going to be a vertical stretch / compress. And how do you know if you have a stretch? Do you know how you know when you have a stretch versus a compress for verticality?
Is it when C is greater than 1?
Correct. Good job. So this is when C is greater than 1. And a compress will be when C is between 0 and 1. Does anyone want to ask the obvious question of what happens if C is negative? No. Because maybe it's obvious to you that we handle the negative case down below. So that negative part is going to be a vertical reflection. Okay. So if the C is inside the function, then that becomes a vertical, and that becomes a horizontal thing. So we got a horizontal stretch / compress. And do you guys know when we have a horizontal stretch?
It's the opposite, right? Like when it's
That's
less.
right.
Yeah.
That's right, Samantha. Yeah, for sure. So I just wanted you to say it instead of me, but it works the exact opposite. So one of the things that you'll notice is that the horizontal stuff and the vertical stuff, they kind of act in the opposite way. Okay. Then when you have a negative all the way on the outside, that's going to be a vertical reflection about the x-axis. And when the negative is inside the function, that's a horizontal reflection about the y-axis. Okay. So I guess there's a natural order that you want to do these guys in. So let me tell you about the order. So the first thing you got to do is you kind of want to have it as well, I'll just tell you the order, I guess. We do the horizontal stuff first. So the first thing you do is you do the stretch. And the second thing you do is you do the reflect. And then the last thing you do is you do the shift. Okay. And for the vertical stuff, you got to do the stretch first, then the reflect, then the shift. Okay. So things should be done in that order. So I want us to look at example 5. I haven't forgotten about example 4, but once we are comfortable with shifting things around, example 4 will be easier for us. So I think when you guys look at this, you guys should be able to tell me the different transformations that we want to do in the correct order. So what's the first transformation I want to do?
The reflection across the y-axis, or no, sorry, x-axis.
Reflection across the x-axis. So I want to do the horizontal stuff first, and horizontal stuff happens inside of the function. So I guess the first thing I'm going to notice is that my basic graph is y is equal to absolute value of x. And what I'm going to do is I'm going to sort of use a sequence of transformations to graph it. So if we're doing horizontal things first, when I look at this, there's only one horizontal action because there's only one thing inside the absolute value of x. So what do you think that first transformation is going to be? Alice says left 3. And I agree. Remember, things work opposite, right? So if you add 3, you're actually going to go to the left. So this is going to be left by 3. And this is going to look like y is equal to absolute value of x plus 3. Okay. Then what am I going to do third? You know, now we've taken care of all the horizontal stuff. So now when we look at the vertical stuff, now we do the vertical reflection. So this will be vertical reflect. And then you're going to get y is equal to negative absolute value of x plus 3. And then the last thing that you're going to do is you're going to do the shift. So it's going to be down by 2. And then it's going to be y is equal to negative absolute value of x plus 3 minus 2. Okay. So we are going to graph each of these things, and we get something nice at the end. So we discussed last class that the absolute value kind of looks like a V. So here's one leg of the V. Here's the other leg of the V. And it's kind of nice for us to keep track of some points. So let's keep track of 0, 0, because that's easy. Normally I might do 1, 1, but I don't want my graph to be too crowded. So let's do 3, 3. And then let's keep track of this side as well. This will be negative 3, 3. Okay. So how do I shift left by 3? Well, if I'm shifting left by 3, all you got to do is subtract 3 from each of the x values, right? So when I subtract 3 from each of those x values, I'm going to get negative 3, 0, like this. I'm going to get 0, 3, and I'm going to get negative 6, 3, like that. So then when we go and graph our first transformation, it looks like this. Does that make sense? Maybe I should say subtract 3. I'll write that in here. Subtract 3 from x values. When I want to do the vertical reflection, I mean, I know you guys can eyeball it, but sort of mathematically, what are we trying to do? We are multiplying y values by -1. So let's keep track of our points again. So this 0, 0, the y value 0 times -1 is just 0. But the 3, 3 point goes to 3, -3, right? And the -3, 3 point goes to -3, -3. We could draw each leg. So this goes like this. This guy goes like this. Okay.
Wait.
Well, it looks better than that.
Oh, sorry. For step number 3, would we reflect step 1 or 2?
Step 2. I reflected the wrong thing.
I wanted to make sure.
I would try to pretend like that was a that's kind of no, you're right. I'm gonna put it in here and I'm gonna shift it. Give me 1 second. How come I can't? My OCD is kicking in. Oh, it doesn't like me. Oh well. You're right. My bad. Off of graph 2, so just shift it over like this. Sorry, gotta start over. Thank you. So this is going to be -3, 0, and then the 0, 3 becomes 0, -3, and then the -3. I'm sorry, the -6, 3 becomes -6, -3, and then you got to draw the 2 legs. So this guy goes like this. And this guy goes like this. Okay. And then thank you for that. And then the last guy, we just got to subtract 2 from y. So I take each of those y values and I subtract 2. So we're going to get -3, -2. And then we're going to get -6, -5. And then we're going to get -3, -5. I'm sorry, 0, -5. Let me graph that. Like this. Okay. And that's our final graph. Does that make sense to everybody? Any questions about that? No. Cool. All right. So I don't know if I want to do this next one. How are we doing on time here? 3:15. I even copied the question wrong. Maybe let's skip that. What was this guy here I wanted you to graph? It's gone. Do any of you guys have this is the classwork number 4. Does anyone have that on them? On their paper? Do you know what I'm asking? Yeah, say it again.
Gx equals negative and then rad. And in the rad, it's x minus 1. and outside of it's +2.
Perfect. Thank you. I want you guys to try this. So take a second to try to graph this guy. If you get stuck, reach out to me. Don't just sit there and wait. I can give you hints or whatever. But try to graph this number 4 and let me know what you get. Good. $325, got it. All right. People are slowly finishing. Just do the best you can, right? All right. Let me reshare my screen here. So this is what I got. My curves are not so pretty. Oh man, I went left instead of right. Oh, it's all wrong. No. Ah, that was bad. Let's see what they said in the chat box. They're laughing at me. This is wrong. This is wrong. It was wrong at the second step. So I don't want to waste time doing the whole thing, but I'll tell you what the transformations are. And then you can I'll also show you what the final answer is. So
I just have like a really quick question.
ask.
When you're doing the radical functions, does it really matter where you put the points as long as it looks like a radical function, or is there like a specific points it should be at, like with the absolute
That's a good
value?
question. So you should keep track of some points, so then you know like I find it's easier to sketch the graph if I keep track of one or 2 or 3 points usually. So I would keep track of a few of them. As far as which points to keep track of, I try to choose easy points that aren't too close together. So like I was trying to keep track of 0, 0, 1, 1, and 4, 2, because I know the square root of 4 is 2. And then once I've established those 3 basic points, I just keep track of where those guys shift to. Does that make sense?
Yeah, that makes sense. Thank you.
Okay, great. So, man, I apologize for that. But the correct order is you got to go right 1, then you do the vertical reflection, then you go down 2. Okay. So let me show you the graph on Desmos, just so you could check your answer, and I don't have to regraph every step because I think that's boring to watch. So we got y is equal to, we got a negative, you got the square root, we're going to have x minus 1. You got to go outside, and it's plus 2. Is that right? So this is what your graph should have looked like. Did you get something like this, Catherine, or are you crying?
I did, but it was a lot more curvy, less straight than that. But does that particularly matter?
I got you. Right. So I think if you sort of kept a hold of 3 points, it would look closer to the thing.
Oh, I did keep hold of 3 points. It's just that the 3
Perfect.
points I kept hold of are curvier than that looks.
I understand. Okay, cool. Okay, so that was great. So now let's go back to the thing that I was originally talking about. Oh, I gotta switch the captioners. I almost forgot. 1 second. Kate. Yes, okay. So the hard part for a lot of students is doing this piecewise defined function. But for us, it's not going to be so hard. And what I suggest is you graph, how do I put this? You graph each function, but you only graph each function on its domain. So there is erasing to do. Okay, so let me show you. how I would do this question. When you look at this first guy over here, what kind of object is this top function?
A line.
That's a line. What's the slope?
1,
And what's the y-intercept?
0, 2.
0, 2. I love how you gave the x value as well. That's so good. For sure. So we can graph the line like this. If you're using pen, don't be too fast to graph. If you're using pencil, you could graph as fast as you like. So I don't know if you could tell, I just labeled the y-intercept. I'm going to have my slope coming up like here, like this. Okay. So this is our equation of a line, the equation of this particular line, right? But what's the domain here? The domain here is only for values less than 1. So what I want to do is I want to erase all parts of the graph where x is not less than 1. So I'm going to come over here. I switch my eraser to partial. I'm going to erase all of this stuff because it's out of state. All of these guys are like outside the domain that we're working with. And you see how we have this less than here? That less than means we're not including 1. So I'm going to put an open circle here. Is there any questions about that? Okay. So when you look at this next guy over here, this second guy, how would you describe this function? Any thoughts?
A quadratic.
Benny, you gonna say something?
A quadratic.
Quadratic, that's right. Is it shifted in any way? Is this a shifted quadratic? Someone just say it. Put me out of my misery.
To the right too.
Yeah, exactly. Quadratic, shifted, right. So when we go ahead and we try to graph this guy, it looks like this. It's shifted right 2, so maybe it looks something like this. Okay. But again, we want to erase all the parts that are outside of that particular domain. So in this case, the domain for this piece is x values that are greater than or equal to 1. So for sure, we want to keep the part where it's equal to 1. So we're going to keep that closed circle there. But then we're going to erase this part right here. So this is the graph of our piecewise defined function. Does that make sense to everybody?